Okay, so just to do a recap of where we are. Uh, we right now we are doing the network layer, and as I said earlier, two primary functions in the network layer are routing and forwarding. So what we did earlier was we looked at routing, the abstract principles behind routing, the different kinds of routing algorithms, link state routing, distance vector routing, and then we looked at how routing is instantiated on the internet, hierarchical routing, routing between autonomous systems. Now when we come to forwarding, forwarding in principle seems very simple. You have a routing table, you have destination nodes, let's say D1, D2, D3 at a router, and you have number of outgoing links. So forwarding in principle seems very simple. You have a routing table, and you have destination, and then you have interface. So 1, 1, 2. So given a particular destination, this routing table will tell you which interface to forward the packet to. So does this seem simple, or do you see any complexity there? Could there be problems? On the face of it, it seems a very simple task. You have a table, you're given a destination in the packet header, you simply put it on the appropriate link. However, the situation is quite complex when we deal with routers, the core of the internet, and the problem arises because of the way addresses are assigned, networks are defined, destinations are defined on the internet. So when we are dealing with forwarding, I'll sort of invert the process a little bit. When we dealt with routing, I first explained the abstract routing principles. To explain the principles behind forwarding, we'll first look at the internet addressing structure. Once we have an understanding of the internet addressing structure, then we can sort of understand the problems associated with forwarding, and then we'll come back to the principles behind forwarding. So to address problems with or issues with the addressing structure, let's first look at how addressing is instantiated on the internet, and to do that we have to understand IP. Okay. So we have all heard of the term IP and IPv4, IPv6. One of the design philosophies of the internet is the so-called IP hourglass. So what's an IP hourglass? Well, we know what hourglass looks like. On the internet, protocol stack, IP resides at the thin portion of this hourglass. On top, you have your complex applications, let's say www, email. You have your protocols, application layer protocols. Then you have transport protocols. Below this IP layer, you have data link protocols. So CSMA, Ethernet, we'll come to all that. And then you have the physical technologies which run these data link protocols. So fiber, copper, radio. And the principle behind this IP hourglass was to keep IP as simple as possible. All the complexity lies below or above IP. IP itself is kept very simple, hence it resides in this thin portion of this hourglass architecture. And IP is the glue which can let all kinds of different technologies come together into one network. So if you have your cell phone, your PDA, your laptop, all of them can talk to each other because all the different complexities below this hourglass are hidden by IP. Once they run IP, they can talk to any other device which is running IP. So you can have all sorts of complexities below IP, all sorts of complexities above IP. IP itself was designed to be very simple. So that you might hear the term often, the IP hourglass. So now let's take a look at IP, the Internet Protocol. So we'll look at what are the service characteristics of IP. We already have some idea. We said earlier that UDP is a stripped down IP. We'll look at the datagram format. Then we'll come to IP addresses, and more specifically IPv4 addresses, because that's what we are dealing with in today's internet. I'll come to IPv6 in a later lecture. We'll look at how IP addresses were assigned originally and what were the problems associated with that. And then we'll come to how IP addresses are assigned now, which is this system called classless interdomain routing, or CIDR or CIDR. And because of this CIDR or CIDR, forwarding becomes a little bit complex, and we'll see what the process of forwarding is. So we know where IP resides on the protocol stack. So IP will add its own header to a TCP segment, TCP or UDP segment. It lies below transport and above link. So the IP datagram considers the whole TCP segment, including the TCP header, as the data. So if you have a device which is operating at the network layer, it will look only at the IP header. It's not going to go down into the data and look at what the TCP header looks like or what the UDP header looks like. So a typical router on the internet never looks beyond the IP header. Everything below that is data. From the application's point of view, this is not data. But at the network layer, everything below this IP header is data. So what are the characteristics of IP? It's connectionless. What that means is that it's not a reliable stream or a stream-oriented protocol. Because it's connectionless, because packets could be individually routed, this property of it being connectionless may lead to missequencing. You might receive packets at the network layer out of order between sender and receiver. It's unreliable. So IP gives you no guarantees of reliable delivery. IP might drop packets. IP is best effort. We'll come to that a little bit later, what I mean by only if necessary. There are some variations introduced an IP which take it to a level above best effort. But for now, let's assume that IP is best effort, and IP is a datagram format where each packet is going to be individually routed, as opposed to being a virtual circuit framework where all packets in a flow have identical routing. Here, every packet of a flow might get routed differently. This is what the IP datagram looks like. The header has a field. This field is versions, which specifies whether this packet is IPv4 or IPv6. There was an IPv5 too, short-lived. Maybe I'll come to that sometime. Header length describes what the length of the header is. You can have optional headers beyond the required headers of the format. So this header length will define whether there are any optional headers associated with this packet or not. TOS are the bits assigned for type of service. So with type of service, you can take IP a little bit beyond best effort. So you can have some sort of priority associated with these packets by appropriately setting the type of service bits in these packets, and then if the router has that capability, it might treat those packets differently. Total length defines the total length of the datagram. It can never be more than 64 kilobytes, including the header. So header plus whatever TCP headers, UDP headers, application layer headers, and the data in a single IP packet has to be less than 64 kilobytes. Every IP packet has this field called IP ID, and that's very important. IP ID is important because packets on the internet, as they go from hop to hop, might get fragmented. And once they get fragmented, they're not reassembled inside the network. The responsibility of reassembling those fragmented packets lies with the end host. So for an end host to reassemble fragmented packets, it's important to know which original packet this fragment belonged to. So for that reason, IP ID is important, because a packet which is sent out from any node on the network can get fragmented. It can get broken into multiple pieces. Source address, destination address, we know what that is. Checksum, again we know it's a method of error checking. Hop count, time to live, we know what TTL field is. TTL field is decremented every time a packet goes from one IP layer device to another. So when it goes from one router to the next, this TTL field is going to be decremented. Once the TTL field reaches 0, then this packet has to be dropped. So that's a feature of IP, and it's used in a clever hack by the program traceroute. Protocol defines which is the transport layer protocol carried by this IP datagram. So UDP, TCP, that is defined by this field. So now let's look at fragmentation. Each link on a path on the internet or any network has this parameter called maximum transmission unit, which is the size of the largest packet that that link can support. Now different links on the path of a packet might have different MTUs. As I said earlier, the specs for IP define the maximum size to be 64 kilobytes. So an end host in principle can send out a packet which is 64 kilobytes. But if the link on which the packet is traveling has an MTU which is less than your original packet size, then that link is going to chop up this packet, is going to fragment that packet into different pieces. So your original packet which had the IP ID field set to X will be broken down into different packets, where the first packet will have the same IP ID field. It will have offset equals 0 and more fragments equals 1. So that's an indication to the end host that this is not the complete packet that was sent. More fragments are going to arrive. Offset equals 0 indicates that for this IP ID, this is the first portion of that fragment. And this carries on until you get to the last piece of this fragment, where you have offset greater than 0 depending on how many chunks it was fragmented to, and more fragment is set to 0. Is there a problem there? Okay. So fragments are reassembled by the destination host only. The network does not do anything apart from possibly fragmenting it. Fragmentation, although it can be solved at the end host, most hosts use this technique of path MTU discovery to avoid fragmentation, because it does cause some performance problems. So typically a host will find out the smallest MTU along a path, and once it has discovered what the smallest MTU is, it will never transmit packets which are larger than this smallest MTU. Most links in today's networks have an MTU which is greater than 1500 bytes. Earlier the Ethernet limit used to be 1500 bytes, but that's no longer a limit. So fragmentation is not really a problem in today's networks. You rarely have packets that get fragmented, but when it was originally designed IP, it was assumed that the packets might get fragmented. So all the pieces are there to solve the problem if you encounter it, but in today's internet you rarely encounter this fragmentation problem. Yeah. There are many ways of doing it. You can probe. You send a probe packet, and at the destination you can detect whether it was fragmented or not. And you keep on sending probe packets until the maximum size packet which is not fragmented.
How, I mean, like, you can reserve, I mean, like, you have certain bandwidth, but then how do you determine, like, what the maximum packet size is that you can send?
I'm not sure I understood.
I mean, like, let's say the MTU is 1500 bytes. That means you can't send packets above 1500 bytes.
Yeah, but it doesn't say 1500 bytes per second.
Right.
That's just the size of the packet.
Right.
Okay.
That's what I'm wondering is how do you determine the size?
Well, you send a 2000 byte packet out, and at the destination you can detect whether it was fragmented or not. If it is not fragmented, then you know that your MTU is at least 2000 on all hops of your link of your path. Yeah.
Does each packet contain different
Well, you assume that your routes are reasonably stable. Yeah, each packets can potentially take different routes. But one thing is that you assume your routes are relatively stable, and the second thing is that a common assumption is that the type of links that you encounter on your path remain constant. So even if you have multiple routes, it's not that suddenly you'll go from a fiber link to a wireless link. The type of links present in both routes or different routes are likely to be the same. So once you have discovered the smallest MTO, you can use that. Now let's look at IP addressing. IP address, or the IPv4 address, is a 32-bit identifier, and this identifier is not for a network node, but it's for an interface on the node. So if you have an Ethernet card, a wireless card, then each of those different interfaces on the internet will have their own IP address. So one particular node can have multiple IP addresses. So in this network that we see here, there's a router sitting in the middle, and this router has 3 different IP addresses. Because it has 3 different interfaces that's connecting this router to 3 different networks or 3 different LANs. This interface is the connection between the host and the physical link. So the physical link could be an Ethernet link, could be a wireless link, any sort of link. The data link protocol typically runs on the interface. The IPv4 address is commonly written down or used in this dotted quad format. So the 32 bits are broken down into 4 8-bit pieces, and you write the address A.B.C.D, identifying those 4 8-bit pieces. So 223.1.1.1 consists of these 4 sets of 8 bits. This is also called the dotted quad format. Yeah.
I believe when you have like for example, a simple network in your home, where you have a router that splits a connection among, like an Ethernet router that splits a connection among multiple hosts, for example, within your home, that router, assuming it's like dynamic IP addresses, may have its own IP addresses, but then each of the hosts behind it will also be assigned an IP address?
Yeah.
But those IP addresses for each host are not unique, right? Because
we'll come to that. So IP addresses also, there are certain classes, certain addresses reserved in this IPv4 family as private addresses. So within your network, those addresses are going to be unique.
But in general, there are these other hosts that have the same IP address.
Not in the same network.
But within another network, you can have, if there's another home, for example,
So all those homes, those private networks, have to run, those addresses that are assigned are private IP addresses. So any address that you see of the form 10.x.x.y.z or 192.68.a.b, these are private addresses. They are required for any node which runs the internet protocol. These addresses are required for every node, even if they are in a private network. But these addresses are not supposed to be leaked out from this network.
how would you contact one of those private?
So you can only contact one way. We'll come to this this issue in a little bit. This is also what's called NAT, network address translation. Yeah.
NTU, you asked the question, can you determine a situation where NTU might be less than 1500 bytes? Do you think it's like a mobile device? Or what is it?
Well, the MTU is a characteristic of the link. So if a mobile device is using a wireless link, and that wireless link does not allow packets which are 1500 bytes, then you can detect that. And the Unix tools that you can use to detect that, look at traceroute or ping. If you do a man for those tools, you can see that you can set the size of the packet that is sent out with those tools. So choose a destination on the internet, set the size of the packet to some really large value, and if the MTU on that path is the smallest MTU is smaller than this packet size, then you'll see an error message. And you'll see that the packet is getting fragmented. So you can use some tools to probe the internet and discover this MTU. So that private address issue we'll come back to in a little bit, and that again is related to how the IP addresses were assigned originally. So originally, when ARPANET or the internet was being developed, there were 5 classes of IP addresses: class A, B, C, D, and E. Class D is reserved for multicast addresses. So these addresses are not associated with individual interfaces, but with multicast groups. When we come to multicast routing, you'll see what that means. So class D was reserved for multicast, class E is reserved for other purposes. For all intents and purposes, any IP address that you had fell into one of the 3 classes: class A, class B, and class C. And the way the whole address space is divided, you have 2 raised to 32 different unique addresses, 32 bits. Class A in class A you fixed 8 bits of the address. In class B you fixed 26 bits of the address, and class C you fixed 24 bits of the address. So what that meant was, if you had a class A address, 8 bits were fixed and 24 bits are free. So a class A address corresponded to a network in which you could potentially have 2 raised to 24 different hosts. A class B address belonged to a network in which you could have 2 raised to 16 different hosts. Class C, 2 raised to 8 or 255 different hosts. So this was the original demarcation of the address space. And when an organization joined the internet, it was assigned one of these 3 classes, depending on the size of the network that was joining the internet. So you got a class A address, class B address, or a class C address. Yeah.
Even if the highest order bits are 110, then it's a class C address, so you should need the next 21 bits as a network ID.
Originally, yeah. So a class B address, the first 2 bits are always 10. The next 14 bits will define which network this class B address belongs to. Yeah, so every class A address will have the first of the dotted quad numbers less than 128, just from those bit assignments. Every class B address will have the first dotted quad number between 128 and 192. So just by looking at this address, you can you can figure out whether this machine belongs to a class A network or a class B network or a class C network. So MIT was originally assigned a class A network. So if you look at the IP addresses of machines on the MIT network, you'll see they're of the form 18 dot blah blah blah. Similarly, I think Stanford is 12 dot something something. Columbia was assigned a class B address. So we have 128.59, and then everything else is free after that. So the first 16 bits were fixed, 128.59, and then we had the freedom of assigning the rest of the 2 raised to 16 addresses to individual hosts. So what's the problem with this kind of assignment? Well, these classes are too rigid. For most of these organizations, class C is too small. So if I'm Columbia, I'm joining the internet, class C will give me a block of 255 or 256 addresses. That is too small for a network of the size of Columbia, the size it's expected to grow to. Class B might be reasonable for Columbia, but let's say you're some medium-sized company and you're assigned a class B address. That address space is going to be too large for that company. So class B is too big, class C is too small. You end up getting assigned class B and you don't use all those addresses. So the address space usage becomes very inefficient. You quickly run out of networks. The other thing is, if you're an organization with internal routers, you would need a different network ID for each of those links. So suppose remember what I said earlier, your routing table has these destinations D1, D2, D3, D4, etc. And associated with these destinations, you would have different links at the router. Now suppose this is the gateway router of Columbia. Okay. Now we have one link going to the main campus, one link going, let's say, to the Lamont Doherty campus, and one link going to the Washington Heights Med School campus. So these are three different networks. Now if these three networks are to be identified in the routing table as separate destinations, then you would need a separate, let's say, class C or class B address to uniquely identify these networks at the router. So to build up this routing table consistently, each of the destinations have to be a valid network, class A, class B, or class C. So if you have an organization which is spread out like this and you need to serve different physical locations, different campuses, so you need your own router, then for each of those locations you would have needed a different network, and that leads to further inefficient use of the address space. You quickly run out of networks. So two solutions were proposed. One solution is called subnetting, and that's used within a single organization. The other solution, which is CIDR or classless interdomain routing, was introduced in the early 90s for address assignment on the internet. So this is a solution which assigns address to organizations. This is a solution which, given an address block, will help solve a problem within an organization. The basic idea behind both is the same. So CEDAR is also called supernetting. The idea between CEDAR and subnetting is very similar. So CEDAR is sometimes referred to as supernetting. And let's see what subnetting looks like. So now imagine you have a class B address, you have some company. You have been assigned a network ID. So the first 2 bits are fixed, the next 14 bits refer to your network. These 16 bits are fixed. Now you can play with the next 16 bits. So what you're going to do is within your organization, you're going to identify different subnets. So you define one subnet ID which uses 20 bits. So the first 16 bits were fixed by the address block allocated to you by the internet. You fix the next 4 bits, and that defines a subnet. Now within this subnet, you have the freedom of choosing 2 raised to 12 different hosts. So you have defined one subnet like this, another subnet like this, with different bits for those extra 4 bits that you are using to define the subnet. So now your subnet is defined by the first 20 bits. And within each of this subnetwork, you can have 2 raised to 12 different addresses. So now, instead of needing different class A, class B, class C addresses here, you have different subnets as the destination. And once you have these subnets, you can further divide that subnet. You can fix more bits. So when you started with this subnet, you fix the first 4 bits to be 0. Within this subnet, you can have another subnet. The only point you have to remember is those original 4 bits are also fixed, and then you're fixing 2 more bits. Now you have a network within this subnet where you can have 2 raised to 10 different hosts, and you can have 4 such networks. And here you can have 16 such networks. Same idea goes through here. So this is the idea behind subnetting. You assign a block of address, then you start fixing bits in the block that you have been assigned, and you assign each of those sub blocks to different networks or subnetworks. So this is the way you have partitioned your class B address into smaller networks or smaller nets. So this is a solution which is used within an organization. The same idea can carry through on at the internet level. So another thing is that, as we saw, that subnetting is a form of hierarchical routing, and you can identify which subnet your machine is on by identifying a subnet mask. So if you're logged on a Unix machine, let's say that any of the cluster machine, and you run this command if config -a, it will give you all the configurations associated with all the interfaces connected to that machine. So one particular interface which has an internet address 128.59.16.5 has a net mask FFFFF800. This net mask identifies that the first 21 bits are the subnet ID. So this machine belongs to a subnet in which you can potentially have 2 raised to 11 different machines. So those are forming their own network. So all destinations within that address space are a single network. They all belong to the same net. So this FFFF800 gives you the mask of the network. 0, 0 and 3 bits here identify the 11 bits that are free in this network. So net mask gives you a way of identifying the size of the subnet. You can also represent this subnet by a prefix plus length. So 128.59/16 is the prefix for Columbia and the length is 16 of the prefix. That's identifying the whole Columbia subnet. And this idea is carried forward with Cedar. So now in Cedar what you do is, instead of having these fixed size segments, class A, class B, class C, you again look at the entire address space as a straight line going from 0 to 2 raised to 32 minus 1. The address space is now broken into line segments. Each line segment is going to be described by a prefix of the form x/y. X will indicate the prefix of all addresses in that particular line segment. So line segment is going to determine a network, and it's described in the form x/y. X is going to indicate the prefix. So for Columbia, X is 128.59. Y describes the length of the segment. So actually 32 minus Y indicates is directly related to the length of the segment. The smaller the Y, the larger is going to be your segment. So if you have a prefix 128/8, that will cover a much larger portion on this line segment. So Y indicates the length of the segment. So this prefix 128.9/16 will represent the line segment which contain all addresses in the range 128.9.0.0 to 128.9.255.255. And you have complete freedom of choosing X and Y. In principle, Y can range from 2 to 30 or whatever. Yeah.
So the Y is the length of the prefix or the
Length of the prefix. So the smaller the prefix, the more free bits you have in the 32 bits. So the more addresses you can have. So the smaller the prefix, longer is this line segment. So this 65/8 is going to be longer on this line than 128.9/16 because here you have 24 bits to play with. So 2 raised to 24 addresses fall under this line segment, whereas here it's only 2 raised to 16. Okay. I'm sorry? So 65/8 indicates that all addresses in this line segment will be of the form 65.x.y.z. The first 8 bits are fixed and they correspond to 65. Rest of the 24 bits are free. So they correspond to individual nodes or individual addresses in this line segment. It's like a class address. It's a class address. And now you have a lot more flexibility. You're not restricted to /8/16/24. You can have /19/17/13. Yeah.
Discussed last week, like 14 for Colombian, translate into these Cedar addresses?
These collection of Cedar addresses. So 14 is Columbia. So Columbia is 14 and it corresponds to all addresses of the form 128.59/16. And also you have your wireless network on. I forget the exact address, but it's 172.84, I don't know, something of this sort.
So there's a couple of,
So you can have different prefixes corresponding to an autonomous system.
somewhere there's a mapping.
And that's where is the routing table. That's what the routing table does. And that's where the problem comes in forwarding. So is that part clear? I mean, there's not a one-to-one correspondence between an autonomous system and a CEDAR prefix. An autonomous system can have a bunch of different CEDAR prefixes. Think of the autonomous system, let's say Sprint, a backbone provider. Sprint will have hundreds, thousands of customers. So it will have a gigantic number of CEDAR prefixes that correspond to its autonomous system. Yeah. Okay.
So when the routing is done, routing is done by the autonomous system or by the IP address, by the CEDAR address?
At the router level?
Right, so if a router knows that it has a packet testing for 128.59/16, it's going to look for the autonomous system number 14, or it's going to look, when do you use the 14 and when do you use the 128?
So you never sort of, you don't directly use 14. So 14 is used at the BGP level routing. So when we spoke about BGP we had paths like, if you want to go from autonomous system 14 to let's say 2792, that path might look like 14, 195, 2802, 2792, let's say. So what that means is that you have autonomous system 14. This is going to send packets to 195, 2802, to 2792. Now the thing to remember is that these links are really virtual links. The physical links are between routers. So there might be multiple physical links here. Okay? These routers we are going to look at the CEDAR address, right? But they also determine, there is also a mechanism in place which ensures that from here, depending on the CEDAR address, you send it to this autonomous system and not to some other autonomous system which might be connected to this router. So the two sort of come are in play together. The actual forwarding is done by using the CEDAR address, but where it goes, the routing table itself is constructed using both information. Yeah.
Questions. The serial addressing now slowly replaced the old address system of Class A, Class B.
Yeah.
So in this case, when you want to ask for an address, so you go and you say, give me a serial address, whatever, /10, and then the registry will be able to distribute that.
Yeah. Basically, yes.
And how do you base how many addresses do you want? Do you use?
Right. I mean, you approach an organization called ICANN. We'll get to that. The picture I gave earlier was somewhat simple. Why simple? Because you had all these intervals were disjoint. You can have overlapping line segments of this form. So you have a line segment or a CEDAR address 128.9/16, and then you have overlapping line segments 128.9/16/20, 128.9/176/20. So physically these correspond to different networks, right? So how is a router going to resolve when it sees an IP address of, let's say, 128.9.176? Is it going to use this CEDAR prefix? This line segment does fall under this region, or is it going to use this CEDAR prefix? You're going to use the longest matching prefix because that is going to give you the most specific route. So again, think of this as let's say 128.9/16 is assigned to Goldman Sachs. That organization has got this prefix. Now it has two offices, one in New York, one location in New York, one location in San Francisco. And now it's done its own subnetting, and New York is 128.9.16/20 and San Francisco is 128. Now someone from Kansas is trying to send a packet to the San Francisco location. So that router from Kansas can send, let's say, the packets. It has two links, one going westbound, one is going eastbound. If it's trying to send this packet to the San Francisco location, then by matching the longest prefix on its routing table, it will send the packet westbound. Yeah.
Isn't it possible may only be seeing this table 128.9?
I'm sorry?
Isn't it possible may only have its table 128.9/16?
Well, then that means that its best route to Goldman Sachs, it has only one route to Goldman Sachs. So this is a router in, let's say, Kansas. What about a router in Australia or Japan? That router, for the, as far as the larger picture of the network goes, for that router, these are in the same general region. So it's highly likely that the same link, the same transatlantic link or the same trans-Pacific link is going to carry traffic for both of them. So in that router, you won't have entries for both of those prefixes, but you'll have an entry only for the higher level prefix, the higher CEDAR address, and it will route according to this address. So depending on the routes that you have at a router, you can have different destination.
Keep the shortest prefix with different interfaces.
You can have different subdivisions, different overlapping line segments, and the rule remains the same. You take the longest matching prefix that you have on your routing table and choose the route corresponding to that longest matching prefix. So CIDR lets you do prefix aggregation. So one example we saw, so the Kansas router had the routing table entries corresponding to both of these prefixes. right? Now let's say this Kansas router is connected to a router in Japan, some satellite link. As far as this router is concerned, both of these addresses are going to go on the same link. So what this router can do is it can aggregate these two CEDAR addresses and advertise only the aggregated address to this router. And you can do that for, you can imagine that for ISPs. You have an ISP which has two different clients and it has assigned these two networks 128.9.14/24, 128.9.15/24 to different customers. And this ISP is the only gateway of these customers to the internet. Then for the rest of the internet, this ISP will only advertise this CEDAR prefix as the address, as the destination prefix. Because as far as the rest of the internet is concerned, to get to any of these, you have to go through this ISP, and so this ISP will only advertise aggregated prefixes. What's the benefit of aggregating prefixes? Yeah. Smaller forwarding tables, smaller prefixes to match, so faster matching. So whenever you can aggregate, you should aggregate. Also, once let's say you are the customer of some ISP and you get assigned this block of addresses. Tomorrow you decide that this second ISP is giving me much better service or cheaper rates. CEDAR lets you keep the block of addresses that were assigned to you. So those IP addresses, they might be hard coded, or it's difficult to move these addresses suddenly. What you can do is you can move your organization to a different ISP, but you can take the address block that was assigned to you. So Columbia, for instance, we have had a number of different providers for the same 128.59 block. And our block just keeps getting moved from Broadwing to Sprint to AT&T, depending on who the provider is. And the routing tables get updated, they get reflected on which autonomous system this block is connected to. Uh-oh. I downloaded an image a couple of days ago of the size of the routing table at the core of the internet. So a router at the core of the internet, how many different prefixes it has in its forwarding table. So it's roughly 170,000 different prefixes. I need to download a different image. Yeah.
I'm not clear about /20 address name scheme. Can you have 128.9.16 and 128.9.176/20 as a valid address, and if you are using only first 4 bits, can you have 176?
Yeah.
And 16 also?
Yeah, it corresponds to different sets of those first 4 bits. Just write out 176 and 16 in bit notation and you'll see. 16 would be 0000. 176 is what? 128 plus 32 plus 16. They do correspond to different addresses. What is the prefix length distribution at a typical core router? So you see that most of the prefixes in the forwarding table of a core router are /24 addresses. So about 60,000 of the prefixes correspond to /24. You have some /23, 22, But the thing to note is that this gap between 16 and 24 has been well filled. There are a number of different networks with a different slash address from 16 and 24. Before CEDAR, you were restricted to 16, 24 or 8. Now you have a better distributed network address space, and so IPv4 space is being utilized more efficiently. So how does a host get an IP address? Well, suppose your network has been assigned an IP address block, then either you hard code this IP address by editing some configuration file, or what's now typically done is you get an IP address through DHCP. DHCP is a dynamic host configuration protocol. The DHCP, in your network typically you have a DHCP server. So when a host wants an IP address, this host will broadcast a DHCP discover message. The server will respond with an offer message, and it will assign an IP address to this host. Now this IP address is dynamic. Once this host gets disconnected from the network, this IP address can be reused. So when you have when you're on the Columbia network with a wireless laptop, every time it gets connected to the internet, it gets a fresh IP address, and that IP address is assigned by the DHCP protocol. So these slides explain the workings of the protocol. Now the next question is how do you get that block of address to begin with? So now we get every machine that's connected to the internet is going to get an IP address from its ISP. For us, the ISP is Columbia. How does the ISP get a block of address? It's assigned this block of address from this organization called ICANN, Internet Corporation for Assigned Names and Numbers. So ICANN does a number of different things. It allocates addresses, it will manage the root DNS servers, it assigns domain names, it resolves disputes. Often there are domain name disputes, there are people who register domain, and then there are copyright issues. All those issues are resolved by ICANN. And ICANN also has delegated local assigning to regional authorities. So ICANN is the higher level authority for the whole of the internet, and then there are 4 different local authorities. ARIN is the American region, Wrttp is for Europe, APNIC is Asia Pacific, and LACNIC is Latin America. So countries which fall in these different regions contact, or ISPs in these regions contact these organizations to get a block of address, and then they can allocate from their block different nets or subnets to their customers. Yeah.
This example that you have Goldman Sachs, they have 128.9. If for some reason they move their headquarters to Asia, something like that, are they still able to keep their block of
Once it's
address?
been assigned, then yeah. But I mean, of course, it will cause all sorts of problems in the routing tables of different routers. So it might be a better idea for them to get a local block just for efficiency purposes. But nothing in the architecture prevents them from moving this block. Yeah.
I mean, once you get this block, then how do you assign address to various machines? Is it centralized, or is it like just put just like a routing table and the router?
So then every organization has freedom to do what it wants to do. Like at Columbia.
How do they assign
Right, at Columbia we have this organization called ACES, which manages the whole Columbia network. Now ACES has delegated subnets to computer science, to EE, to business school. So within computer science, CRF decides the allocation. So you just delegate it to different networks, and within the network you can do whatever you want. That's not really a technical issue. So, do you have questions on the IPv4 addressing? So now after going through this, do you have a sense of what a routing table in a core router would look like? So a routing table has destination and interface for the forwarding. So what do destinations look like? These destinations are going to look like and so on and so forth. And we could see the figure earlier, but from the distribution of the prefix length, we get a sense that a core router might have 170,000 or so such entries. And then you have a prefix, the interface, 1, 1, 2. So now, when a packet arrives at a router in the core, it's going to look at the address. It has to go through this table, which potentially contains 170,000 entries, do the longest prefix match, and come up with the right interface. We can imagine that this problem is not very simple. Yeah.
That moves from America to Europe. The Japanese routing table would probably just update the interface number from, let's say, 1 to 5 or whatever.
Probably, yeah.
So it gets notified of that by propagation, is that?
You get notified of it by BGP, yeah. So now what will happen is Goldman Sachs, let's say, was autonomous system 851. When it was in North America, it was connected to 2329, which is Sprint. So the paths that were advertised on the internet, on BGP, to reach Goldman Sachs, you had 2329, 851. Now Goldman Sachs moves to Australia, and this ISP is now Telstra, which is 476. Now BGP is going to talk to all other BGP routers on the internet and update this path. Now routers on the internet, they will update the interface according to the direction where which the links take you to 476 as opposed to 2379. So in some ways the move is transparent. You have just moved this whole block, connected to a different autonomous system who's your provider. And then BGP will take care of the rest. So then,
To get to 476 now, it just use such and such an interface.
yeah. So what? So BGP, yeah. So the router here will start advertising that to get to 851, come to me. I have a one hop path. And it does that by advertising that this prefix, I don't know what I wrote earlier, belongs to me. So it's still done through the prefix which maps onto an autonomous system. But this, the routers here are going to do that job. And other autonomous systems which are connected to this will have a 2-hop path to 851. So routers here, if they have autonomous systems here, if they have a choice of going this way or this way, typically they'll choose this path. There might be policies which might prevent them from taking this direct path. But once it has advertised that there is a direct autonomous system level path, then you take that path. But note that this one hop path might be going through 20 different routers. Because what's being routed within that autonomous system is hidden from the rest of the internet. So in the next lecture we'll take a look at what a modern router looks like, how forwarding is done, what are the techniques that are used to speed up this search or matching operation in a routing table.